Now, projectile motion was studied extensively from the 17th century on, because they had all the mathematics they needed to analyze the trajectories of cannonballs. And people were shooting a lot of cannonballs at each other in those days. There were a lot of wars in Europe and in other parts of the world, but especially in Europe, where this science of shooting artillery, and there's a name for that. And, okay, I don't want to take time to stop and think about it. It'll probably pop in my head. Okay, that was studied extensively. Now, when you lob a cannonball at somebody, once the cannonball is out of the cannon, the only force acting on it is the gravitational force and air resistance. Okay, we're going to ignore air resistance because that's the first thing we do. Okay, if you shoot a cannonball, there is some air resistance. It does have a definite effect on the path of the cannonball, but it's not a huge effect. So what you do is you figure out where the cannonball would land if you put a certain amount of powder in, if you angle the thing at a certain angle and use a certain kind of fuse. You figure out how fast the cannonball is going to come out of the cannon, and once it's out of the cannon, you assume that it's moving just under just the influence of gravity, which is pulling it downward. So if it's going up, which it pretty much always will be, you very seldom shoot a cannonball downward if you're on a hill, then it's going to slow down as it rises. It's going to rise more and more slowly, and it's going to start falling, but at the same time it's moving this way. Okay? Those two motions are regarded as independent. They are independent. They're at right angles to one another. And you calculate where the cannonball would be if there was no air resistance. Then you do some corrections for air resistance. We're not going to talk about that except conceptually. So an ideal projectile is that cannonball moving in a vacuum. Now, if you're in a vacuum, you and your enemies are already dead. So that's not really going to happen. The cannonball would be redundant, and besides, your powder wouldn't burn. Okay, now, I illustrated this by attempting to toss a piece of chalk into the trash can. Now, this one's going to go in, I guarantee it. Yep. Now, it hit the back rim and bounced in, so it was kind of nothing but net. But it actually went in because my shoulder's looser now than it was this morning when I kept missing. I have direction control. Okay. Now, we used that as a first idea for a projectile. So it wasn't a cannonball, it was a piece of chalk. I didn't do any calculations, but the piece of chalk isn't moving that fast. Air resistance doesn't have all that much effect on its motion, but it does have a tiny effect. Might make a centimeter of difference. I don't think it would make much more than that, but that's just an intuitive guess. Okay, so we estimated how fast that thing was moving. I don't think we estimated real well. Most people kind of overestimated how long it takes the chalk to get to the trash can. Now, you saw when it left my hand, and you heard when it hit. So you could actually, with a stopwatch, make a pretty good estimate of how fast it was moving. In class, I was about 4 meters away from the trash can. To get in front of the camera, I was about 3 meters away. So it traveled 3 meters in the horizontal direction. So by timing, you could use that to get a good estimate of the horizontal velocity. Anyhow, I chose the estimate 6 meters per second, which is a little higher than the estimates most people made, but a lot of people thought it took about a second to get there. It didn't take a second. It was less than that. Turned out this is actually a pretty good model for coming at least reasonably close to the trash can. We only overshoot it in this model by about a meter. Okay, well, projectile 37 degrees above horizontal. That's just an estimate of the angle at which the chalk left my hand, okay? And you actually saw that. You could probably make a better estimate. But 37 degrees is not unreasonable. So, here's our initial velocity. Now, I did ask people for initial velocity, and people wrote down speeds. They didn't write down velocities. Okay? And people should know what a velocity is by now. And a velocity has to have a magnitude and a direction. So 6 meters per second, but you got to tell me at what angle. Okay? So 6 meters per second, 37 degrees above horizontal, that's a velocity. 6 meters per second is a speed. Here's a picture. Okay, our x direction is regarded as horizontal. And of course the trash can is this way, and now I'm modeling it in this direction, but I'm modeling it as a person standing behind the board would have seen it if they could see through the board. Okay, so there we have it. Well, the x and the y motion in this case are as independent as they were in this model for the ship. So everything we did here could apply here. All we have to do is figure out our initial x velocity, our initial y velocity, and we can model the motion from there on. Of course, we have to use the acceleration of gravity, but we know that. So 6 meters per second at 37 degrees, we project that velocity on the x-axis. Well, the angle between the velocity and the x-axis is 37 degrees, so it's pretty clear that our projection on x, which would be what I would call our initial x velocity, is 6 meters per second times the cosine of 37 degrees, which comes out 4.8 meters per second. It's convenient that the cosine of 37 degrees is very close to 0.8, not exactly, but very close, and the sine of 37 degrees is very close to 0.6. Again, not exact, but very close. So, to a good approximation, multiplying this by this, we get 4.8 meters per second. Our y velocity, initial y velocity, and that could be our y0x, is our projection of this vector on y. Now, I didn't write out all the details, projection of v0 on the I vector, let's say. I could have written it out like that, but we understand what we're seeing here. So, our initial x velocity is this, our initial y velocity is this. Here we have it. And if we wanted now, we could get the equation of the y versus x parabola. Okay? And we could then determine the position of the trash can and see if our parabola intersects the position of the trash can. Okay? That'd just be an exercise in pre-calculus. We could do that, and sometimes we kind of need to do that. Like, it's very convenient to be able to get at the equation of the parabola if we're asking, okay, now I'm projecting a cannonball up a hill. Where's that cannonball going to land? The parabolic path of the cannonball will intersect the equation of the hill. So you have two equations, you set them equal, you find where they intersect. Okay, that's an important technique for some problems and for some problems that you are being assigned. Okay, so we could do that. Once we know our initial x velocity, our initial y velocity, and our initial position and so forth, we can get our y versus x parabola and compare that with the shape of whatever we're trying to hit. Find the point of intersection. We don't need to do that here. Here, we just have to ask, okay, well, in this case, the target was not 3 meters away, it was 4 meters away. How long does it take? Now I'm over here a meter in this direction, and I, toss the chalk. How long does it take that chalk to get to the position of the trash can? Of course, the trash can has some width, but let's just say it has one position. If it's 4 meters away, well, we're moving at 4.8 meters per second in the horizontal direction. So we can easily determine that it takes what? 4 meters divided by 4.8 meters per second, or 0.83 seconds. Now, we can use the fact that delta t is delta x over x velocity. But that's a very straightforward calculation in this case. It's not always straightforward. You'll see a couple of cases in a minute that aren't. Okay, so your delta t is about 0.83 seconds. Now that we know delta t is 0.83 seconds, we ask ourselves, well, okay, now what's the value of y when t equals 0.83 seconds? Well, we plug in, we have our acceleration, which is the acceleration of gravity, so 1/2 of the y acceleration is, using the 10 meter per second squared approximation for convenience, we get -5 meters per second squared. Did I say meters per second? -10 meters per second squared. So we get -5 meters per second squared times t squared. Maybe a little hard to read because I didn't write down my t squared when I wrote this down. Realized when I got down here I needed t squared. Okay, units wouldn't have worked out, and besides I know darn well there's a t squared there. I knew I needed it when I got down here. I didn't see it up here, so I had to squeeze it in. Okay, so we get this, plus our v naught y times t, 3.6 meters per second times t, plus our y naught, which is 0 presumably, assuming implicitly that we start at 0.00. Well, then we just evaluate that for the given value of t. So we replace t with 0.83 seconds, we do the calculation, and we see -0.5 meters. Now what does that tell me? Well, I draw a little picture. I could show you that if you were in class. It means that we're 0.5 meters lower than where I released the chalk when we get to the position of the trash can. Now, unfortunately, it turned out the trash can was about a meter below the vertical position, okay? So it's about a meter below, so I would have gone 1/2 meter above it, which is kind of a bad miss from this direction, but still not all that far off. Okay. So what's this say? This says, now let's assume I'm here and the trash can is over here. I release the chalk here, and the trash can is here. This is 4 meters from here over to here. And I release the chalk and it follows this parabolic path like so. And when it gets to the position of the trash can, actually I didn't do a good job with that. Okay? When it gets to the position of the trash can, it's lower than it was when I released it, but it's still above the trash can. I still don't have that path drawn very well because I'm looking at a weird angle. That's what these calculations tell me. I didn't have to get the equation of the parabola, though, to see that. Okay, sometimes I need to get the equation of the parabola. Okay? So, this tells me that if I had started at this velocity, 37 degrees above horizontal, a meter above the trash can, by the time I got to the trash can, my y position would be 0.5 meters lower than I started, and that's too high to hit the trash can. Okay? Think of this within the context of this whole picture.